Welcome to Math with Professor V. In this video, we're going to learn about the tabular method for integration by parts. This method is sometimes also called the DI method. It might have other names, but basically it's a way for you to organize all of the information or components that go into our by parts formula into a table. Now, when can you use the tabular method? Always. You can always use it. However, it works the best with certain kinds of integrals, and we're going to examine those carefully. What are these kinds of integrals where you especially want to use the tabular method? It's anytime you have a polynomial function times any other function that you can easily integrate repeatedly. Okay, so when you have an integral involving the product of these two kinds of functions, let's think how we would normally want to set up integration by parts. We would have our polynomial most likely be u, and then the other function that we could integrate along with dx or d, whatever the variable of the integral is, that would be dv, right? And hopefully by now you've seen sometimes it takes more than one round of integration by parts. You have to apply it 2, maybe 3 times, maybe more. And in that case, it can be a little tedious to keep track of everything. So that's when tabular really comes in clutch. So what happens is whatever u would normally be, you put it in the first column that we call d, and then whatever dv would be, that function, the other function that you can easily integrate, goes in the column for I. And I'll just basically explain the process by working through an example with you because that's just the easiest way to do it. But the beauty is that you can just apply repeated rounds of integration by parts here by differentiating until you hit 0. That's the goal. Okay. Now, sometimes you won't hit 0 in that D column, and that's okay. I'll show you what to do in such a scenario and how you can always use tabular if you just fall in love with it so much. All right, first example. Let's just do something to get warmed up to see exactly how this method works. We have indefinite integral of x times cosine 5x dx. So think how you would normally set up integration by parts for this. You would pick u to be x and dv to be cosine 5x dx, right? Well, instead, if we're doing tabular, I'm going to make 2 columns, d and I. Whatever u would normally be goes in the d column. And then whatever dv would be goes under the column for I. You don't have to put dx. Let's just put cosine 5x. Okay, so this is to remind us we're going to take the derivative. We're differentiating x and keep going until you get 0. That's when this works the best, if you can get a 0. So derivative of x is 1, and then derivative of 1, 0. So I'm done. I had to differentiate twice. That tells me now this column I need to integrate the same number of times. I need to integrate cosine 5x twice as well. Just be careful. So let's think backwards. Whose derivative did we take to get cosine 5x? It would have to be 1/5 sine 5x, right? Because remember, when we differentiate, if there's a constant in front of the variable, you multiply by it because of the chain rule. So when we integrate, we have to go the other way. We're going to divide. So I have 1/5 sine 5x, and it's positive. Oh yeah. And then one more time, whose derivative did we take to get 1/5 sine 5x? Negative 1/25 cosine 5x. Beautiful. Are you guys okay? All right, now from here, to put together our final answer, we take these diagonal products. So you take the entry on the left and you multiply it by the entry in the column on the right, 1 row below. So we're going to multiply these 2 entries and multiply these 2 entries. And then we have to alternate signs on these products. So I'll explain why in just a second, but just hang tight. So this, we always start with positive. You don't change the sign on that product. Then on the next product, you're going to add an extra negative. You're going to switch the sign of that product. And then if I had more entries, I would repeat the process. So you would have plus, minus, etc. Okay? Again, I'll show you why in just a hot second, so hang tight. And now we're ready to write our final answer. Can you believe it? Quick and breezy. So this is going to give me 1/5 x sine 5x, keep the sign the same, so 1/5 x sine 5x, and then the next product, be careful, so you have negative 1/25 cosine 5x, and then we also multiply by another negative, so now it becomes positive 1/25 cosine 5x, and then you just have to remember to put plus c since this was an indefinite integral. And we are done. That's it. Okay, so what exactly is going on? Well, let's just think what would happen had we proceeded with our normal integration by parts method or formula. Well, you would find du, which is just 1 dx, and then you would find v, okay, 1/5 sine 5x, and that's exactly what happened in this second row, right? 1 dx, here it is, 1/5 sine 5x, here it is. And then what do? You do take this diagonal product, don't you? Yes. You have 1/5 x sine 5x, but what do we do next? We do minus integral of this product right here, which is 1/5 sine 5x dx. Well, instead of resulting in having to do one more integral, we took care of it right here, but this minus sign needed to get distributed, so that's why we added it at this step. And what happens is when you keep doing integration by parts over and over and over, you have these nested negative signs that keep having to get distributed. And so the table helps you capture that. Just remember that the signs start with the positive, then you have minus to capture this minus, then the next one would be plus because you'd have two minuses, and so on and so forth. Okay? Now, when I see that it's only going to take one round of by parts like this, I don't always jump to the tabular method. But if you love it, go for it, okay? Why not? Who's to stop you? Hopefully not your professor. Okay, let's move on to another example where it's especially satisfying. Like I wouldn't even think to do regular integration by parts. When I see I've got polynomial degree 2 and a trig function, boom, straight to tabular. Okay, here we go. So di. You want the D column to go to 0 if possible. I'll show you what to do when it doesn't later, but let's just practice getting good at this first. So in the first column, I'm going to put x squared plus 2x. I know if I take enough derivatives of that polynomial, it'll go to 0. And then I've got cosine x in the next column. Okay, here we go. So derivative of x squared plus 2x. 2x plus 2. Good job. Keep going. Derivative of 2x plus 2. 2, yes. And one more time, derivative of 2, 0. Okay, so I took 3 derivatives. Now I need to antidifferentiate 3 times as well. So antiderivative of cosine x, sine x, very good. One more time, negative cosine x. Last time, negative sine x. Beautiful. Okay, now we're going to take diagonal products. So draw your little arrows. I got 3 of them this time, and the signs alternate. So plus, add an extra negative, don't change the sign, okay? So here we go. We've got x squared plus 2x times sine x squared plus 2x times sine x. Then the next diagonal product, 2x plus 2 times negative cosine x, but there's another negative, so then that's going to be positive 2x plus 2 cosine x. And then last product is 2 times negative sine x, and we don't change the sign, so it's just going to be minus 2 sine x plus c. Okay, you know the back of the book left it like this, and I said shame on them. I don't like it. Because see how this term involves sine x, this involves cosine, and this also involves sine x? Why don't we put these guys together? That way this poor little negative 2 sine x isn't lonely over here. I feel sorry for it. So x squared plus 2x minus 2 sine x plus, and then we can leave this all together, 2x plus 2 cosine x plus c. I think that looks so much better. What do you think? Let me know. I was feeling bad for the little negative 2 sine x over there. Okay, good. No, you don't always have to do it with the trig function. Tabular would work beautifully on this following integral. Integral of z cubed e to the z dz. You know what I recommend? I recommend you pause the video, you try this one on your own, see how good you are. I think you probably can do it. I have a good feeling about this. Okay, di I. In the D column, I'm going to put z cubed, and then I'm going to integrate e to the z. If you haven't started crossing your z's yet, think about it. Seriously think about it, because you might confuse it with a 2. Especially if you're going to take multivariable. You're going to be writing a lot of z's in the future. Okay, derivative of z cubed, 3z squared. Excellent. Keep it going. We're not at 0 yet. Derivative of 3z squared, 6z. Again, 6. And then finally, at long last, 0. Okay. Now we can integrate e to the z. Oh, this is relaxing. Look at us here. E to the, it's easy. Okay. That was a cheesy joke, but you know, I'm a math professor. I'll take what I can get. Okay, now we take all these diagonal products. Ba-dum, ba-dum, ba-dum. Draw your little arrows, and then the signs alternate. Always starts with a positive, then negative, then positive, then negative. Okay. So here we go. Let's put it all together. Z cubed e to the z minus 3z squared e to the z plus 6z e to the z minus 6e to the z plus c. Could you leave it like that? Sure, but I would say let's factor out e to the z because it's in every single term. So e to the z times z cubed minus 3z squared plus 6z minus 6 plus c. And then we are done. Fantastic, fantastic. Okay, now the last 2 examples I'm going to show you involve integrals in which this first column is not going to become 0, but you could still use tabular, okay? Now, this particular integral here I love so much. It's one that boomerangs. Boomerangs in the sense that you never actually integrate. You don't explicitly find the antiderivative. You use the fact that after 2 rounds of integration by parts, the original integral reappears. It comes back to you like a boomerang you sent out into the wild, and then you can solve from there. So hopefully you've seen a problem like this. If not, I've solved one on the Integral of the Day playlist, so I'll link it in the description if you want to see the traditional way of solving it, not using tabular. But I'm going to use tabular. In this case, like the derivative of e to the 2 theta, we know that'll never be 0. In fact, it's cyclical, right? It's always going to be e to the 2 theta, and then we're just going to keep multiplying by 2's. And then similarly, sine 3 theta, its derivatives are also cyclical. It'll jump between cosines and negative signs and whatnot, but it'll just keep coming back and cycling through. It's never going to be 0. But what we can do is just use the tabular method to organize the process of integration by parts repeatedly happening. Okay, so here's what you do. Pick somebody to be D and pick somebody to be I, and in this case it doesn't matter with these boomerang ones. So I'll put e to the 2 theta here and sine 3 theta here, but you could switch them, okay? And then what you want to do is differentiate and integrate one at a time, because we know we're never going to hit 0. So derivative of e to the 2 theta is 2e to the 2 theta. And then antiderivative of sine 3 theta would be negative 1/3 cosine 3 theta. Now, should I stop here? Normally, this is one round of integration by parts. You would have, this is uv minus integral v du. Here's the integral v du. Has my boomerang come back to me? E to the 2 theta cosine 3 theta. Is that what was in my original integral? No. Don't worry about the constants. We're cool. Just are the 2 functions. What did my integral return? Not yet. So keep going. So derivative of 2e to the 2 theta would be 4e to the 2 theta. Never mind that aircraft flying. I don't know what it is. Okay, and then antiderivative of negative 1/3 cosine 3 theta. That's negative 1/9 sine 3 theta. So what you would do, if you were to keep using this table, you'd have this product, and then you'd have minus this product, and then we would have plus this integral. The sign switches. So it would be minus this integral, but if we stop here, it would be plus this integral. The signs switch. This integral, the product of e to the 2 theta and sine 3 theta, is that my original integral coming back to me? Has my boomerang returned? It has. Don't freak out that there would be a negative 4/9 in the front. That's fine. That's good enough. We can take that outside of the integral. So this is where I'm going to call it. We stop here. It's enough because my boomerang has returned. So you take this diagonal product here. You take this diagonal product here. This one's going to be plus. This one's going to be minus. And then we're going to have plus this integral. Oh, yeah. Okay. Remember, normally it would be minus this integral. That's why it's plus this integral. So it switches as well. Here we go. My original problem, e to the 2 theta sine 3 theta d theta, that original integral is equal to negative 1/3 e to the 2 theta cosine 3 theta. Watch out. 2 times negative 1/9 times another negative now gives me positive 2/9 e to the 2 theta sine 3 theta. Are we okay? And then this is negative 4/9. Let me take that outside. Times the integral of e to the 2 theta sine 3 theta. You just got to remember to add that d theta. Okay? How are we doing? Good. I wrote a little crooked. Please forgive me. Okay. Now, here's our boomerang returning to us. I'm going to call the original problem, the original integral, I. And here it is. Here's I coming back to me. So if you've never seen this before, what happens is we just treat that integral, the antiderivative that we're finding, as some variable quantity that we're solving for. So I could rewrite this as I equals negative 1/3 e to the 2 theta cosine 3 theta plus 2/9 e to the 2 theta sine 3 theta minus 4/9 I. Now, if I told you, hey, solve for I, get it all by itself, what would you do? Hopefully you say, I would add 4/9 I to both sides, yes, add 4/9 I. Right now I have 1I plus 4/9I. This is 9/9I plus 4/9I. That's 13/9I equals negative 1/3 e to the 2 theta cosine 3 theta plus 2/9 e to the 2 theta sine 3 theta. I still need to get I by itself, so multiply everybody by, that's it, the reciprocal, 9/13. And then now I have I equals negative, I'm going to distribute 9/13 and 1/3, that's going to give me 3/13 e to the 2 theta cosine 3 theta plus this is 2/13 e to the 2 theta sine 3 theta. Technically, right now we should put plus c, right? And it feels funny, like we never actually did the integral. You know what I mean? Explicitly. But add it right now because we found its general antiderivative. And then let's clean it up. I don't like leaving I equals in my final answer because we came up with I. Let's respect the problem. Let's rewrite what it was at least. E to the 2 theta sine 3 theta d theta equals, let's make it cute. Let's clean it up. I can factor out e to the 2 theta over 13. And then let's put the positive 1 in the front. What do I mean by that? Put 2 sine 3 theta first minus 3 cosine 3 theta plus c. You know, at this point in your math career, you should appreciate, right? Like, this is so much more aesthetically pleasing not having this ugly little negative out front. Blech. Okay. Are you proud? Let's box it with pride. Fantastic. I have to say, when I first learned about these kinds of integrals, it made me upset that we couldn't just directly go in and integrate them and that we had to do it this way. I felt somewhat like a cheater, but now I embrace it all, you know. Are you bothered? Let me know. Okay, one more where I'm going to show you, you can use tabular always for by parts, but it's not always great. It's just not. But if you're diehard, I'll show you how to make it work. So here we go. So D has to be something you can differentiate, and I has to be something you can integrate. Like, we cannot integrate ln of x easily. In fact, we find its antiderivative using by parts. So that's not going to go in the I column. I'm going to put it in the D column. Let's put ln of x squared in the D column. And then I is just going to be 1. Now, I already can tell that the derivative is never going to be 0, right? So take the derivative of ln of x squared. It's 2 ln of x. And then by the chain rule, you have to multiply by derivative of ln of x, which is 1 over x. So this is all divided by x. And then integrate, antiderivative of 1 is just x. Okay. Should we keep going? I don't think so, because I don't hate integrating this product. The x will cancel. We're going to have to do by parts one more time, but you do need to actually compute this product in order for things to simplify. Watch, this is not going to be helpful. If I kept differentiating, we would have to do the quotient rule, wouldn't we? So you would have low d high minus high d low. I'm singing the song, guys. That's how I learned the quotient rule over 20 years ago, and it's still working for me. Over low low. So what is that? 2 minus 2 ln of x over x squared. Okay, if I anti-differentiate one more time, now it's 1/2 x squared. Is it any better? Is it any better? Because wherever we decide to call it, you have to integrate that horizontal product, right? Would you rather call it here or here? Nothing got better. We got an extra term, if anything. No. So I say abort mission. I say abort mission after the one standard round. So really, you could have just used regular integration by parts, not tabular. Not tabular. But maybe you just don't like writing out u and dv. I can respect that. Okay. So what would happen in this case? So you have this product, and then you have minus that integral. You just got to add that dx. Okay. So this is x times ln of x squared minus integral 2 ln of x. Those x's cancel, right? So I'm not even going to write them. Dx. But then we're not done. We need to do by parts one more time on this guy. Again, you could set it up u and dv, or if you really, really want, we can do tabular again. So whoever would normally be u, that's d. So let's put 2 ln of x here, and then 1 dx is I, and then derivative of 2 ln of x, that would be 2 over x. Antiderivative of 1, just x. So we've got x ln of x squared minus, and then here we have this product, keep the sign the same, minus this integral. So it would be 2x ln of x minus integral 2 over x times x. The x's cancel, so it's just 2. Don't forget to write dx. Good. You ready? We're there. X ln of x squared minus 2x ln of x. Antiderivative is going to be 2x. This minus and this minus sign cancel out, so then it's just plus 2x plus c. So hopefully you could see in this last example, right? If you keep going, it's not going to get any better. So you're going to have to call it just after this one round. But if you would just rather write d and I instead of u and dv and use this to set up your integration by parts, you're more than welcome to. It's always available to you. And then in those super beautiful instances where this column will go to 0, then of course, I really encourage you to use the tabular method. It'll also, in addition to saving you time, save you the possible error of forgetting to distribute negatives and constants and whatnot, because it really does just organize everything so succinctly. So I hope you enjoyed the video. I hope it cleared up some questions that you might have had about the tabular or DI method. And don't forget to give the video a thumbs up. Subscribe to my YouTube channel if you haven't already. If you need help with any of your other calculus topics in your courses, then you've come to the right place, because I have video lectures on almost every single topic in Calc 1, 2, and 3, as well as pre-calc, trig, intro to stats, just to help you lay any foundation